All right, this is a problem on our practice sets, and we do see several that are very, very similar. The key to working these problems is we're looking for patterns. So let's back up a bit and talk about the patterns. If you know that you have a first order process, that means the rate law looks something like this, where A is your reactant, a reacting species, and it's raised to the first power. That means as you change the concentration of the species A, since K stays constant, your rate is also going to change proportionally as long as you stay at constant temperature. And we always assume constant temperature unless you're told that the temperature changes. And so if the concentration of A doubles, that means the rate will also double because it's first order. If now all of a sudden I have twice the value in A, when I calculate rate with the same value of K, I'll get twice the numerical value for rate. If the concentration of A triples, and it's first order, this assumes that I am first order, then the rate goes up by 3 raised to the first power, so the rate also triples. So the pattern we see for a first order is that the rate does the same thing that the concentration does. If the change in concentration is by 27, that means the rate will also change. It'll go up by 27 because that's the pattern. If I have a second order, the pattern is different because the rate law is different. If I have a second order reaction, that means the rate law looks like this. We're making the assumption we have a very simple rate law in terms of one reacting species at this point. So what happens to the concentration, if I change the concentration, now the rate is going to change by that amount squared. And so if the concentration of A doubles, then the rate will change by 2 squared, or it'll go up by 4. If the concentration of A triples, the rate will go up by 3, because that's how much the concentration went up by, squared, because it's second order, and 3 squared is 9. If the concentration goes up by 27, then the rate is going to go up by 27 squared. So it goes up by whatever the concentration goes up, raised to whatever the order is, and I need to use my calculator. 27 squared is 729. So that's the pattern of a second order. The pattern of a third order is different. If I have a third order process, that is because, and again, we're assuming one species, rate is equal to K times that concentration raised to the third power. And by the way, a reaction is either first order or second order or third order. It doesn't move around. It doesn't change. I'm using A for all of these, but I'm obviously talking about 3 different reactions because a reaction can't be first order and second order and third order. So these are different reactions. But we see the pattern that if it's third order, then we have the concentration raised to the third power. And so if my concentration doubles, then the rate is going to go up by 2 raised to the third power. And that's by 8. If the concentration triples, then the rate is going to go up by 3, because that's the concentration change, to the third power because it's third order. And 3 to the third power is 27. So the rate goes up by 27. If the concentration goes up by 27, then the rate goes up by 27 cubed. And I have to punch that in. Or it goes up by 19,683. So those are the patterns. And there's one last pattern. It's a very simple pattern. If I have a 0th order, a 0th order means that the concentration is raised to the 0th power. Anything raised to the 0th power is 1. And so as I change my concentration, if the concentration of A goes up by 2, the rate goes up by 2 raised to the 0th power, or the rate goes up by 1, it stays the same. If the concentration goes up by 3, the rate goes up by 3 to the 0th power, which is equal to 1, which means the rate stays the same. If the rate stays the same as I change the concentration, I'm looking at a 0th order. So those are the patterns I have to keep track of. Those are the patterns I have to be able to recognize. Now, if we come back up to this problem, you'll notice, first of all, there are 2 reactants. There's an X and there's a Y. Now that I have 2 reactants, the pattern can get more complicated, and so I simplify it in my experimental trial by keeping something constant. If I keep a reagent constant, so for example, as I look here from trial 1 to trial 2, trial 1, I put this stuff in a container. If we think about experimentally, what this means is I dump together X and Y such that I have 0.03 molarity of X, 0.02 molarity of Y, and I measure the rate and I get that it's 2.76 times 10 to the minus 3 molarity per second. I ran that trial. Then I emptied the container and started from scratch and ran trial 2. And you'll notice when I picked the concentrations, because I'm adding this stuff so I get to pick, when I picked the concentrations, I kept Y the same. That's so I can ignore it. Whenever I keep something the same, it is not affecting how that rate changes, no matter if it's first, second, third, or 0th, it doesn't change the rate because it's staying constant. So the constant, the guy who stays constant, I can ignore between trials 1 and 2. Sorry. Okay, so I can ignore those between trials 1 and 2 and focus on what is changing. And what is changing is X. So that's what I'm focusing on. And so what I want to look at is what pattern do I observe. So as X changes, you'll notice it goes by 3. Between 0.03 and 0.09, it went up times 3. And if you're ever not sure, if you need to calculate it by hand, sometimes the numbers get messy, I can check that by taking 0.090, the larger one, divided by the smallest one, and that tells me it goes up by 3. All right, so you may need to check it if the numbers get messy. Now I want to see what the rate did. So that was the concentration of X. Now I'm going to look how the rate is changing. And again, if you're not sure about the numbers, take the second one, divide by the first one. And you're always taking the larger and dividing by the smaller just to keep from having fractions. And I take 8.28 times 10 to the minus 3 divided by 2.76 times 10 to the minus 3, and I get 3. So concentration changed by 3, rate changed by 3. What pattern is that? That's the pattern of a first order process. That means, therefore, the concentration of X will be raised to the first power. Now I check Y, and I want to check Y, how Y affects the rate. A change in Y affects the rate. Let me put this way down here. All right, I'll check that by keeping X constant. Again, if I keep something constant, I can ignore it. So as I look, X stays constant from trial 1 to trial 3. So what I want to look at is what does Y do? So from trial 1 to trial 3, the concentration of Y went up by 3 again, and again I can check that 0.06 divided by 0.02, which went up by 3. So the concentration of Y went up by 3. Now I want to see what the rate did. So as I go from trial 1 to trial 3, the rate went up by how much? And again, if I can't see it in the pattern of the numbers, I take the larger, divide by the smaller, and see what I get there. And I get 8.9855, and I think you can see that that pretty much rounds to 9. I get that the rate goes up by 9. So I have the scenario where the concentration goes up by 3 and the rate goes up by 9. What pattern is that? And just to remind you, the rate is equal to the constant K times the concentration of Y raised to that order. So the rate went up by 9. That's comparable to the concentration going up by 3 watt. 3 raised to watt power. That's what I'm looking for. I'm looking for that order. And 3 squared is 9. So 3 squared, which means it's second order. So my rate law will be K times, and we discovered that X, X is, yeah, X, we looked, did I do that? No, we were looking at X first, and we discovered that X was first order. And now we see that Y is second order. So that would be the rate law for this. If it required a numerical value of K, if I need K, solve. Take the data, and you might need K, the rate constant. Use the data for one of the trials, plug into that rate law, and solve for K. So I would plug in the value of the rate. So 2.76 times 10 to the minus 3 equals K times the concentration of X, and X was raised to the first power, and the concentration of Y, which is raised to the second power, second order, and I solve for K. And I can double check that with trial 2. I should be getting the same K. I can double check that with trial 3. I should be getting the same K. If I don't get exactly the same K for every single trial, that means my orders are wrong. I hope that helps.